I am Dr. Victor Rivera Monroy, an associate professor in the Department of Oceanography and Coastal Sciences at Louisiana State University, and I am a coastal and wetland ecologist. I also work with the South Central Climate Science Center. In this video, I will discuss some of the most critical impacts of climate change of coastal systems. The coastal ocean consists of highly connected ecosystems that include rivers, estuaries, tidal wetlands, and the continental shelf. Coastal systems are very dynamic regions where the abundant diversity and productivity of natural resources have supported human civilizations for centuries. The abundance of renewable and non-renewable resources in coastal systems has shaped the economy and social organization of human societies around the world. Most of the largest U.S. cities are on the coast, including New York, Los Angeles, Miami, Boston, Seattle, and San Francisco. Marine habitats from the intertidal zone out to the continental shelf break annually provide over $14 trillion of ecosystem goods, like food and raw materials, and services like hurricane protection and nutrient cycling. This amount represents 43% of all global ecosystem services. Climate affects the functioning, distribution, dimensions, and form of coastal and estuarine systems. Climate change impacts on coastal and estuarine ecosystems include accelerated sea level rise, increased air and water temperatures, changes in rainfall distribution and freshwater inputs, and also changes in the frequency and intensity of storms. These effects may become more severe as a result of interactions with other human activities in the coastal regions. The natural variability of Earth's climate system is reflected in the evolutionary adaptation of a species and large-scale patterns of biogeography. Over the past several centuries, human activities have become an additional important component to the climate system. Together, elevated greenhouse gases and their associated increase in global mean temperature will result in a cascade of physical and chemical changes in coastal and marine systems. For example, because warming trends will be stronger over continental interiors than over oceans, scientists project that winds along ocean margins will intensify and may lead to enhanced upwelling of deep ocean water, increasing nutrient availability at the surface. However, a stronger thermal stratification and a deepening of the thermocline could also prevent cool, nutrient-rich waters from being upwelled. Because upwelling is fundamental to maintaining economically important fisheries, further understanding of the relationship between climate change and upwelling is a high research priority. Changes in atmospheric circulation may also change storm frequency. In fact, an increase in the frequency of winter storms has already been observed in coastal oceans, and the trend is expected to continue. However, complex relationships between global warming and multi-year climatic oscillations, such as El Niño Southern Oscillation or the Atlantic Multi-Decadal Oscillation, will undoubtedly have a major effect on storms. Changing precipitation patterns will affect coastal salinity, turbidity, and runoff of nutrients and pollutants from land. Impacts of climate change on coastal and ocean biochemistry are important and very often overlooked. Atmospheric carbon dioxide concentrations are expected to more than double from pre-industrial levels by the year 2100, and about 30% of modern CO2 emissions are taken up by the oceans. Continued uptake of atmospheric CO2 is expected to substantially increase acidity over the next few centuries, reducing the ability of marine organisms such as corals to develop their skeletal structure. This can trigger large-scale mortality of valuable and highly diverse coral reef ecosystems. While many marine organisms have adapted to water temperature fluctuations in the last few million years, the projected changes in ocean acidity are higher than any inferred from the fossil record over the past 200 to 300 million years. Changes in fresh water, sediment, and nutrient delivery in coastal regions are likely to be highly regional. They are also difficult to predict because they will be affected by changes in regional precipitation, ocean circulation, processes that trap sediment, shoreline erosion, and more importantly, in local and regional human activities. Sea level rise, coastal storms, sedimentation, and changing freshwater input can directly influence coastal and estuarine wetlands. And climate change will affect all four of these factors. Direct and indirect impacts will depend heavily on biological processes such as the reduction of water velocity by plant communities that increases sedimentation, below-ground plant productivity, organic soil formation by wetland plants, and changes produced by fauna and microbial activities of resident communities. There is a strong scientific consensus that coastal marine ecosystems, along with the goods and services they provide, are threatened by anthropogenic global climate change. Recent climatic trends have already triggered a significant response in the Earth's biota. As these changes continue, we risk serious degradation of marine ecosystems with far-reaching consequences for human health and welfare. As a result, ecologists like me are focusing our research on understanding and mitigating the impacts of anthropogenic climate change on our coastal marine environments.